The International Network of Algerian Scientists, INAS, is a nonprofit organization founded in 2016 by Algerian academics and professionals residing in the USA. The motivation is to pay back the homeland and help elevate the level of education in Algeria. INAS's mission is to network Algerian competencies worldwide with counterparts in Algeria. Among its activities, INAS has organized a significant conference that took place outside of Washington, D.C., USA in 2019. The conferees identified several need areas in Algeria and agreed to work on 10 different projects covering areas ranging from education, healthcare, to agriculture and ecotourism, to name a few. The work is ongoing and progressing. INAS is adopting the most contemporary and proven scientific methods to address these issues. INAS's humble beginnings included a few members. Today, it accounts for hundreds of able Algerians from the world over. Their goal is to participate in the rebuilding process of our new Algeria. These able and proud Algerians combine diversity and expertise with benevolence to set a path for a bright future in Algeria. INAS uses a top technology platform to allow members to collaborate and exchange knowledge. As an organization, INAS has different departments that ensure professional support to all its members, projects, and events. We welcome all Algerian competencies worldwide to join us in our noble mission.
الشبكة العالمية للعلماء الجزائريين إيناس هي منظمة غير ربحية تأسست عام 2016 من قبل أكاديميين ومهنيين جزائريين مقيمين في الولايات المتحدة الأمريكية. الهدف من وراء تأسيسها هو رد الجميل للوطن والمساعدة في رفع مستوى التعليم في الجزائر. مهمة إيناس هي ربط الكفاءات الجزائرية في جميع أنحاء العالم مع نظرائهم في الجزائر. من بين أنشطتها نظمت إيناس مؤتمرا مهما عقد خارج العاصمة واشنطن في الولايات المتحدة الأمريكية عام 2019. حدد المشاركون في المؤتمر عدة قطاعات حيوية تحتاجها الجزائر، واتفقوا على العمل في 10 مشاريع تغطي مجالات مختلفة، نذكر منها التعليم والرعاية الصحية والزراعة والسياحة البيئية إلى آخره. والعمل في هذه المشاريع لا زال قائما. تستخدم إيناس أكثر المناهج العلمية تطورا من أجل تسيير ومعالجة هذه المشاريع. البداية المتواضعة لإيناس تضمنت عددا قليلا من الأعضاء، وهي اليوم تضم مئات الجزائريين الأكفاء من جميع أنحاء العالم. هدفهم هو المشاركة في رد الجميل والمساهمة في بناء جزائرنا الجديدة. هذه الثلة من الكفاءات الجزائرية الفخورة بوطنها تجمع بين التنوع والخبرة مع الاستعداد والرغبة في تمهيد الطريق من أجل مستقبل مشرق للجزائر. تستخدم إيناس منصة تقنية جد متطورة تسمح للأعضاء بالتعاون وتبادل الأفكار والخبرات. كمنظمة قائمة، إيناس لديها أقسام عملية مختلفة تضمن الدعم المحترف لجميع أعضائها ومشاريعها وتظاهراتها العلمية. نرحب بكل الكفاءات الجزائرية في العالم للانضمام إلينا في هذه المهمة النبيلة. الجزائر أكبر منا جميعا، فلننهض ولنترك بصمة.
We are live, دكتور عبد الحي. We can start إن شاء الله.
السلام عليكم ورحمة الله تعالى وبركاته. مرحبا بكم جميعا مشاهدينا الكرام في هذا البث المباشر عبر الفيسبوك واليوتيوب. اليوم إن شاء الله سنبدأ سلسلة ندوات الويب الخاصة بالفيزياء الطبية. هذا الحدث هو أحد اقتراحات اليوم الثاني للفيزياء الطبية الذي عقد في 7 نوفمبر الماضي بجامعة الواد. ستكون سلسلة الندوات هذه عبر الإنترنت بالتعاون مع الشبكة الدولية للعلماء الجزائريين. كذلك الندوة الأولى إن شاء الله هي حول تنفيذ مدونة الممارسات TRS483 IAEA AAPM بشكل قياس الجرعات في الحقول الثابتة الصغيرة المستخدمة في العلاج الإشعاعي والخارجي. ضيفنا لهذا اليوم هو الدكتور عريب مهنا من المملكة العربية السعودية. دكتور عريب مهنا هو رئيس المختبر الثانوي المعياري لقياس الجرعات. هو رئيس المختبر الثانوي المعياري لقياس الجرعات قسم الفيزياء الطبية الحيوية مستشفى الملك فيصل التخصصي ومركز الأبحاث بالمملكة العربية السعودية. Assalamu alaikum everyone. Welcome to all our dear viewer to this live broadcast on Facebook and YouTube. Today, inshallah, we are starting our webinar series of medical physics. This event is one of the suggested of the second day of medical physics, which held last 7 November 2020 at El-Oued University. The webinar series will be with the cooperation of INAS. INAS is the International Network of Algerian Scientists. Our first webinar will be on the implementation of TRS483 IAEA AAPM code of practice on dosimetry of small static fields used in external radiotherapy. So our speaker is our pleasure to invite to host our speaker, Dr. ARIB Mehenna. He is the head of secondary standard dosimetry laboratory in the Biomedical Physics Department at King Faisal Specialist Hospital and Research Center from Kingdom of Saudi Arabia. Please let us know how it goes and write a comment on Facebook and YouTube channel, and be sure to subscribe on our YouTube channel of INAS and Hello Medical Physics. So you are welcome, Mr. ARIB. And before take the call, Mr. ARIB, Mr. Dr. Ismail, you have the talk in 1 minute.
Okay, thank you so much. So welcome, Mr. ARIB, to our first webinar. It's a pleasure to invite you and be among us to present this kind of webinar. So I'm Dr. Ismail Zawoga, medical physicist from Iran, and I welcome all the person that joining us to this webinar. As it's the first time that we are organizing among all medical physicists in Algeria. So it's our pleasure to share the knowledge between physicists and keep up to knowledge this kind of webinars. So now we can start the webinar with Dr. Mehenna ARIB. So welcome again to this webinar.
Thank you, Hi, thank you, Ismail. Bismillah ar-Rahman ar-Rahim. Salatu wassalamu ala Rasulillah ashrafil mursalin. So, dear colleagues, good morning, good afternoon, good evening, wherever you are in the world. It's a pleasure for me to present this first webinar on the implementation of the new IAEA AAPM code of practice for dosimetry of static small photon fields, TRS483. This webinar actually was decided during the second days of medical physics, organized by the University of El-Oued in Algeria last month. So we decided to go with giving a webinar on specialized fields each Saturday of each month. I have the high honor to start with this presentation. Actually, during the second day, they gave an overview of the results that we have obtained during the testing of the IAEA TRS483 at King Faisal Specialist Hospital and Research Center, and I gave some results for the linear accelerator, variant, and the tomotherapy and cyberknife. I will go now with more advanced webinar and workshops. I have prepared some examples to allow you better understand the concept of MSR and small field dosimetry. As I will show you, these are two different concepts that you have to separate and then you have to understand. So yes, so remember that in 2000, when the IAEA and the AAPM published their code of practice based on the use of absorbed dose to water calibration coefficient, or using based on the use of one ionization chamber calibrated in terms of absorbed dose to water, this protocol was a success story because we were able to measure the absorbed dose to water in most straightforward manner using this ionization chamber. So if you go and measure the dose to water in the reference conditions, which are the SSD, source to surface distance of 100 centimeter, depth in water phantom of 10 centimeter, and a field size of 10 by 10. I put it here in yellow because now we are going to put more attention on the field size. This is the most issue for the small fields, okay? So the formula here written in red is it's very straightforward. MQ is the dosimeter reading at the reference depth, the ref correct for influence quantities like temperature, pressure, electrical calibration of the electrometer, polarity correction factor, and saturation correction factor. And the WQ0 is the ion chamber calibration coefficient at the reference quality Q0. In most cases, Q0 is the cobalt-16. We still use the cobalt-16 to calibrate the ionization chambers in terms of absorbed dose to water. And KQQ0 is a beam quality factor that converts the calibration coefficient from the cobalt-16 to the quality Q. So this, the KQQ0 were measured either experimentally or by Monte Carlo simulation, and the two codes of practice publishes very nice tables and curves giving this correction factor as a function of the quality index. Pay attention again to the quality index. This is one of the important parameters. Then when you measure the dose in the reference conditions, you have to calculate the dose at Z max, which is the depth of dose maximum, using either PDDs or TMRs according to the configuration that you are using. Okay, in the TRS483 and TG51, you have the quality index is given as a function of TPR, which is the tissue phantom ratio at 20 and 10, and as a function of the percentage depth dose at 10 centimeter depth. By the X is just to see that we have to remove the electrons contamination by putting a sheet of 1 millimeter lead to attenuate the electron contamination. Okay. So problem one, the field size here is for the reference conditions is 10 by 10. It is not always possible to get for some specific machines the 10 by 10 field size, like CyberKnife, Gamma Knife, or tomotherapy. So we are already starting by when we move from the usual or usual linear accelerators to the most specific machines like CyberKnife or Gamma Knife or tomotherapy. We have already a problem of the field size. We don't have the 10 by 10. We'll see how to deal with this. And then once you measure the dose to water at the reference conditions, you have to calculate the dose for any other field size just to accommodate, for example, the tumor, which is not necessarily the 10 by 10. In that case, you use what we call the output factor. Previously, we used to multiply the dose in reference conditions for 10 by 10 by the output factor, which used to be determined by the ratio of the dose at the clinical field size divided by the dose at 10 by 10. Since the dose doesn't vary with the field, this ratio of doses can be approximated by the ratio of the readings of the detector you are using to calculate the output factor. When you switch from the conventional field sizes down to 6x6 to more smaller field sizes, if you still apply this output factor for calculating the absorbed dose for small fields, you get differences of up to 50%. This is because of the fact that the ratio of the readings or the ratio of the doses for small fields is not necessarily the ratio of the readings is not necessarily the ratio of the doses. Why? Because when you have a broad beams, the dose depends on two main factors. It depends on the stopping power ratios and on the perturbation factor for the chamber. Use it for that beam. When you have a broad beam, the perturbation factor and this stopping power ratios are quasi-constant. So the ratio of the doses is equal to the ratio of the reading of the detector, of the ionization chamber. When you go to the small fields, the stopping power ratio remains independent on the field size. But the perturbation is much more important for small fields compared to the conventional field. That's why the ratio of the readings is completely different from the ratio of the doses. And therefore, if you apply this ratio to calculate the dose at small fields, you get very high difference in 50%. This is what happened in April 2007 and in 2004, where when the physicists used it to measure the output factor using a large chamber, and then 145 patients in Toulouse, France, were irradiated with completely absorbed doses. So there was what we call, this is an incident actually. This is one of the it's after this incident that the international community started thinking about the dosimetry of small fields. So dosimetry of small fields, and so these are some machines that are not able to get the 10 by 10. You have the CyberKnife tomotherapy, CyberKnife here, and you have here also the gamma knife. So we have the very small field sizes. Okay, so this is just two pictures of the IAEA AAPM working group. Very nice, group who worked on the TRS483, and this is, by the way, this is the first time that the international community, the IAEA, community, and the AAPM sat together and came up with a common code of practice. Each time the IAEA publishes a code of practice, the IAPM publishes a similar one, just with different formalisms and so on. And this is after 10 years of extensive meetings of this group, they came up with this code of practice, very nice code of practice. I hope that you are able to have it. This is downloadable from the IAEA website, free of charge, of course. And after the publication of, just before the publication, official publication of the TRS483, there was one group formed by the International Atomic Energy Agency. I had the honor to be a part of this group. We worked on the testing of this code of practice from different point of view and check if the formalisms are still valid and so on. So we worked from 2015 to 2018, and now where a tech doc published by the IAEA is about to be issued by the IAEA soon. Okay, so the TRS483 code of practice addresses two different things. It addresses the reference dosimetry of MSR fields, and it addresses also the relative dosimetry, or the measurement of the output, the field output factor. By the way, we call it now field output factor, just to make a difference between the previous output factors, as I explained. And this address also the energies up to 10 megawatt. If you want to do the dosimeter of 15 MeV, forget it. It's not yet ready. Just keep stuck on 6 and 10 MeV. Okay? And also, it does not address other radiotherapy modalities such as the electrons, protons, or orthovoltage beams. Okay, so this, as I said, it addresses two different things. That's why the TRS483 is actually 2-in-1. It has two codes of practice: reference dosimetry of MSR fields and relative dosimetry of small fields. That's why you need to separate between the MSR fields and the small fields. Okay, as I will explain in more details now. So the concept of TRS483, it is dealing with the machine-specific reference field, which we call MSR, machine-specific reference field. So the MSR fields, they are used just for reference dosimetry. Okay? Whenever the field size that you have to use, the MSR, the machine-specific reference field, should be as close as possible to 10 by 10 centimeter, or it should be the largest field available in a given machine. Just an example. For CyberKnife, you have different cones. The largest diameter of the cone is 6 centimeters. That's why the MSR, the machine-specific reference field for CyberKnife, is a diameter 6 centimeters. Okay? FMSR, the machine-specific reference field, is not a small field. Why? Because the MSR, as we will see, the MSR field, it should fulfill the lateral charge particle equilibrium conditions, as we will explain in more details later on. The reference dosimetry, in that case, is determined exactly similarly to the TRS483. Okay? Because you have a chamber that is calibrated in different ways, as I will explain, and you use the TRS483. When you switch now to the clinic, in the clinic, you don't have necessarily the MSR field. You have smaller field sizes. In that case, we are talking about small fields. Now we are dealing with the relative measurement, because the reference dosimetry is not done for the small fields. The absolute dosimetry is not done for small fields. It is done for the machine-specific reference field. When you switch to the smaller field size, you have to use the what we call the field output factors, gamma, and which will use also the field output correction factors, as we will see also. Okay. Now, when are we allowed to talk about the small field? So we have three main conditions, three physical conditions. At least one of these conditions should be fulfilled in order for the field to be named small field. The first condition is the loss of lateral charge particle equilibrium. So as you know, when you perform the dose measurement with an ionization chamber, you are actually measuring charges. So you have the charge that is created in the wall of the chamber, okay? And then these charges are electrons. Some electrons, they deposit the energy in the volume, and some of them, they scatter and leave the volume. the quantity that is actually used in the dosimetry is the deposition of the energy is actually the air kerma. It is the kerma because the kerma is the sum of all the energies that are deposited in the volume. The energy that is actually deposited in the volume without the electrons that leave the volume is called the collisional kerma. Okay, there is a condition that the dose and the collisional kerma are equal. In that case, we apply the dosimetry protocols because the lateral charge particle equilibrium is actually a condition in which the electrons that are leaving the volume are compensated by the electrons scattered from the surrounding of the volume. This is the lateral charge particle equilibrium. You see in this figure here that it depends on the energy. For example, for the copper-16, the lateral charge particle equilibrium is fulfilled at a radius of the cavity of the chamber at 0.5 centimeter, just 5 millimeter. Whereas for 24 megavolt photon X-ray beams, you need 2.5 centimeter volume radius to achieve the lateral charge particle equilibrium. So we have, if this condition is lost, then we are talking about the small fields, because the small fields, the charges that are deposited in the volume are not compensated by the scatter, and then you lose the information. The second condition is the source occlusion. In the source occlusion, I will not spend more time in explaining. Just keep in mind that when you look at the source from the phantom, you will see, because the source is not point source, it has some dimensions, let's say 2 centimeters. So the emission of the source is emitting from all the paths from the right to the left, and then because of the collimators, the photons or the photons of the particles that are emitted by the left part is attenuated, or it doesn't reach the phantom, and that's why you have a central part which is in red, in which all the particles are arriving. In the right hand part, you have some kind of penumbra. This is the penumbra actually, because you don't have the maximum of particles coming from the source. When you close the jaws, you don't see the two parts of the source. You see only the central part, and therefore you are actually losing the information. And not only you are losing the information, but because of the penumbra, because the jaws or because of the collimators are so small, the two penumbras actually they overlap. If they overlap, then the concept of field width at half maximum, which is used in the code of practice, the field size is actually determined by the field width at half maximum, but 50%. You will see the field width at half maximum going down. So you lose also the information about the field size, okay? Because the field size is not now defined by the physical dimensions of the jaw. The third condition is linked to the detector size. The detector size, when, for example, the volume of the detector of the chamber is bigger than the shape of the beam, then here you have a problem, because usually when you use the broad beam, whatever chamber you put, the chamber is irradiated by the flattened region of the beam, and you don't have to care about the uniformity of the beam. But when the field is small compared to the dimensions of the chamber, then only one part of the chamber is irradiated by the flattened region of the beam, and the other part is irradiated more or less depending on the dimension, depending on the field size, depending on the beam profile. That's why in the code of practice we are talking about the volume averaging correction factor, which corrects for this fact, the fact that the small fields, or for the when the field is small, only part of the chamber is irradiated. So these are the three conditions. We will not spend more time in this, but let's move to the reference dosimetry. This is the first part of the code of practice, the reference dosimetry of MSR field. So we have three different conditions. You have generators or machines that achieve 10 by 10 field size. In that case, just follow TRS483 or AAPM TG51 or equivalent protocol just to measure the absorbed dot to water. There are some generators, some machines that are not able to achieve the 10 by 10. Either they cannot achieve it, or they cannot. It cannot be set. For example, some machines like CyberKnife, it doesn't have the square field; it's circular field. So in that case, you have to define a machine-specific reference field size. And we will show you later on. The dimension of the MSR field should be as close as possible to the conventional reference field. So you have to select the bigger field size available for the machine. Okay. These are examples of, the fields for common radiotherapy machines. Radiosurgical collimators, 1.8 centimeter diameter collimator. It's far from the 10 by 10. So the Brain Lab micro MLC, you can achieve the 10 by 10 because you have Brain Lab, you have the micro MLC, you can set the 10 by 10. So this is the equivalent square MSR field size is achievable. The CyberKnife, we have different cones. The largest cone is the 6 centimeter. This is the MSR. The machine-specific reference field is 6 centimeter diameter. The Gamma Knife, it's 1.6 centimeter or 1.8 diameter collimator because we have different collimators. Okay, and for tomotherapy, you have the jaws that cannot open symmetrically. You have, so the field size is 5 centimeter over by 10 centimeter. So you can open the jaws in one direction like this. For the other direction, you open it only to 5 centimeters. So this is the rectangular beam. We will see how to deal with this. Okay. Now let's have a look at the reference dosimetry, which I will explain in details. The reference dosimetry is similar, as I told you, to the TRS483. The dose to water. Whenever you have here, for example, for some machines, you can achieve 10 by 10. So you just use the code of practice. Dose, as I started with, the dose is the reading of the chamber multiplied by the calibration coefficient in the reference quality, cover 16, and then multiplied by Q0. Okay, and then when the 10 by 10 is not able to be achieved, like CyberKnife, tomotherapy, and other machines, then you have to think about the hypothetical reference field 10 by 10, just hypothetical, okay, and then apply an additional correction factor, which corrects from the fact that the MSR field is different from 10 by 10. Okay, so they have to switch to the hypothetical, just to use the Q0 for 10 by 10, just use it as intermediate field size, and then apply an additional correction factor. So just, you have a chamber calibrated in cobalt 16 for 10 by 10. You put it in the machine, you calculate the dose, assuming that you have 10 by 10. You apply the Q0 as in TRS483. And then, because I have now field size, MSR field is different from 10 by 10, I apply the last correction factor. And then I get now that, and here you have the Q, MSR Q. This factor is explaining the fact that the energy in the for the MSR field may be different from the Q MSR, okay? Because you have, but in most cases, this is the same energy, okay? And also in the upper part, you have the field size switching from FREF 10 by 10 to FMSR, which is 6 centimeter in case of the CyberKnife. And then once you measure the absorbed dose in MSR field, in reference conditions. You go to the clinic now, you measure, you have to calculate the dose for the F clean. F clean is the clinical field size, which is different from the MSR. Could be smaller, could be different shape, and so on. In that case, the dose in dose to water for the Q clean, for the clinical quality, for the field size F clean is given by the dose that you previously measured for the MSR field, applying an additional gamma factor, which is the field output factor. The field output factor converts the dose from the reference field to the dose to the clinical field. Okay, that's why, and in the gamma, actually the field, the field output factor. Just remember that now we call it field output factor. We no longer call it output factor, just to avoid any misunderstanding or any confusion with the previous output factor, which used to be the ratio, as is shown here, the ratio of the reading for the clinical field size divided by the MSR field size. Okay, so in addition to this, to achieve the gamma, you have to take the previous ratio of readings and multiply by the field output correction factor. The field output correction factor is here just to correct the ratio in order to get the correct feed output factor. Just an example. If you take 3 chambers, you measure the output factors, the ratio of readings, you get 3 different curves. The difference in smaller field size can be as large as 50%. So you need to correct individual for each chamber at any field size. Correct the ratio of the readings by the appropriate feed output correction factor for that field size. Don't worry. The feed output correction factors are published in the TRS483. They're given in form of tables. Okay. So basically, the formalism for absorbed dose to water is summarized here. So now, because now you are, everything is depending on the absorbed dose to water calibration coefficient, which is NDWQ0. Okay. Now we have three main hypotheses, 3 main situations. Assume that you have your chamber calibrated in some lab for your MSR field. Okay, this is rare, but there are few primary standard dosimetry laboratories that are able to calibrate your chamber for the MSR fields. Just ask them to calibrate it for example, for 5 by 10 for topotherapy, they will do it. In that case, you have the NDW QMSR, but calibrated for the FMSR, for your MSR field. In that case, the absorbed dose is straightforward. The dose is the reading corrected for influence quantities multiplied by your calibration factor, which is determined for your machine. You don't have to apply any correction factor because the field size is the same as in the primary lab. The second option is that you send the chamber to the secondary standard dosimeter lab. It is calibrated for Q0 for cobalt 16 for a field size 10 by 10, and then you have to apply the formalism that we explained already. So the dose is reading by the calibration coefficient for Q0 multiplied by the quality correction factor, which converts the calibration coefficient in cobalt to the calibration coefficient in your MSR field and your quality. Okay. In most cases, RF is 10 by 10. In that case, we can remove the FRF and we remove the Q0, and we talk about QMSR, FMSR. Okay. There is, and here the KQ MSR, FMSR is tabulated because they are available. In some cases, they are not available. For example, for some energies, for some qualities, and some fields. In that case, you need just to split the QMSR Q0, FMSR FREF, the last factor here. You split it in two parts. The first part is related to the cobalt-16 and quality Q, keeping the FMSR. As I told you, yeah. This is hypothetical field size, which is KQ-Q0 FMSR. Okay? And then you have a second factor, which converts from the fact that you have different field size and different also energy. Okay? This is really rare. In most cases, you have the two conditions, A and B. Okay. So the KQ, remember here, I told you here when FREF is 10 by 10 and Q0 is cobalt-16, just remove the FREF and Q0 and keep just the factor is called KQ, and also remove the QMSR, it is KQ and FREF. Okay. So for this is given in the TRS483 for the wedged filter for WFF beams. Okay, you can see here the. I will show you that these chambers here, they should fulfill some conditions. So for the MSR field calibration, only some chambers are selected. So you have here, this is given as function of TPR and percentage depth dose at 10 centimeter, and for field size for 10 by 10 and TPR for 10 by 10. Okay, and you have here a table. You have another table here, and you have also here for FFF. So we have the tables available for WFF and for FFF. They are not the same because of the shape of the field size, so the correction factor are different. Okay. This is also just set of data for the gamma knife. Okay. Let me focus a little bit on the yes, and formalism for small fields now. So the formalism for MSR field is very simple. Dose equal to the reading corrected for temperature, pressure, polarity recombination, multiplied by the absorbed dose to water calibration coefficient for the reference quality, cobalt-16 in general, multiplied by the correction factor, which depends on the quality and on the fields. And now when you switch to the small fields, you need to, as I told you, you need to apply the feed output factor, okay, which is the ratio, the product of the ratio of the readings, which is a conventional output factor, as everybody knows, multiplied by the feed output correction factor, which is tabulated also in the code of practice. Okay, now let's go back to the MSR fields for the reference dosimetry. Can I use any chamber just for the reference dosimetry of FMSR? And if not, what is the size restriction on an ionization chamber for MSR dosimetry? I'm still talking about the reference dosimetry. I have plenty of chamber in my department. I bought many years ago chamber. Am I allowed to take this chamber and just go do the calibration of my cyber knife? The tomotherapy, they are calling me. They are asking me to bring my chambers to perform the reference dosimetry of the tomotherapy. What are the restrictions of the chamber? They need to select which are the most suitable for the reference dosimetry of FMSR. This is what I will go and explain. Remember, MSR are not small fields. The MSR fields are the fields that fulfill the condition of the lateral charge particle equilibrium. So we are allowed to use one ionization chamber if the CPE condition is verified. Okay, so what does it mean? That means that when the field, the MSR field, the field size, extends at least a distance of the lateral charge particle beyond the outer boundaries of the ionization chamber, so I need to have a field size that will not disturb the charge particle equilibrium in order for the chamber to measure to be used for this dosimetry. Let's first of all calculate this lateral charge particle equilibrium. What is this Chinese? Sorry for my Chinese friends. What is this statement? Lateral charge particle equilibrium. It has been calculated that the R LCPE in centimeter is given as a function of the quality index or percentage depth dose of 10. It is by a section of TPR or percentage depth dose using this equation here. Okay, don't tell me where it is coming from. It is coming from the curves that I showed you in the beginning. Because the achievement of the lateral charge particle equilibrium depends on the energy. Remember the copper 16 and the 24 MeV. The one is achieved at 5 millimeters, the other one at 2.5. So it depends on the energy. This dependence on the energy is seen here in the TPR or percentage depth. Be careful. This equation, we use the TPR 2010, which is the ratio of the tissue phantom ratios at 20 and 10 centimeters for a field size 10 by 10. The same for the percentage depth dose at 10 centimeters measured for a field size of 10 by 10. Okay, so this just go. Let's take two chambers, okay, and then investigate. Or I will show you here how to calculate or how to check the fulfillment of the lateral charge particle equilibrium for these two chambers. So we have, first of all, we have the dimensions. It is say the FWHM should be more bigger than 2 times the lateral charge particle equilibrium radius, plus D are the dimensions of the chamber. Which ones am I going to use? The longitudinal dimensions, the length, or the radius. Let me calculate and see what happens. In this case, for example, the chamber on the left, the length of the chamber, be careful. You need to take the dimensions of the external, not the dimensions of the volume, the cavity volume, the dimensions of the detector from the outside dimension. Okay. So you see that the length for the chamber in the left, which is the pinpoint, actually, it's 5.7. The diameter of the chamber is 3.4. Which one is big? It's 5.7. So I select 5.7. This is the D that should be used in the equation for FWHM, because the lateral charge particle equilibrium should be fulfilled either in length, in the length part of the chamber, and in the diameter also. It's the same for the chamber on the right. You have 6.8 versus 3.5. So we select 6.8 in the equation. Let me show you now a detailed calculations for the 3 chambers, actually. Let's select the farmer chamber. This chamber is amazing chamber. It is liked by everyone. We like to use it for the reference dosimetry. Let me calculate what is the minimum fields, MSR field, that can be used, for which minimum field size am I allowed to use this chamber? Okay, let's go and calculate the lateral charge particle equilibrium first using the data. So this the drawing here is taken from the PTW catalog, but it's outdated. Actually, the true dimensions are given in red here. The length is 23 millimeter, and the radius, be careful, radius, not diameter. The radius is 3.3. So they are giving here the cavity radius. Therefore, to calculate the external dimensions, you need to add the thickness of the wall, okay, which is here 0.057 gram per centimeter square. I'm already in trouble because it is not millimeter, it is in gram per centimeter square. I will show you how to do it. So let's start with calculating and consider that we are doing a calibration of 6 MeV with a TPR 2010 at 10 by 10 is 0.677. Okay, let's calculate the radius of the lateral charge particle equilibrium radius in centimeter. This is the formula that they gave you. TPR 2010 is 0.677. So you multiply, you use the operation, you just replace the TPR by 0.677, you get 12.8 millimeter. So this is the radius of your lateral charge particle equilibrium. Or the particles beyond this inside this radius are supposed to fulfill the charge particle equilibrium, in which case in this radius the dose is equal to the collisional part of the curve. Okay, now, well, this is the equation. The FWHM, the full width at half maximum, should be bigger than 2 times LCE plus D. So, okay, we need again to calculate, we need to get again to calculate this D using this data from the table. You have the length 23 millimeter, the radius 3.8 millimeter, and the T wall 0.058. If you use T wall is made of PMMA, we know that for this chamber it's perspex. So the density of the PMMA is 1.19. Remember how to calculate the dimension in linear dimension, starting from the mass thickness in gram per centimeter square. You just multiply by the density, because when you multiply the density, when you multiply the thickness in gram per centimeter square, you multiply it by gram, you divide it by rho, which is gram per centimeter cube. You divide by rho, you get centimeter. Okay, so the thickness is actually 0.48. Okay, 0.057 divide by 1.19 is 0.48 millimeter. You get actually 0.048 centimeter. We convert it to millimeter to be consistent with the rest of the dimensions. Now, in the longitudinal direction of the chamber, the maximum the dimensions, because 23 is the length of the cavity. The length of the cavity. You need to add the thickness on the right part. The left part you don't have. You have the stem. Okay, so you add 0.48. You get 23.8448 millimeter. Let's say 33.5 millimeter. These are the dimensions, the external dimensions of the chamber. Okay, this is the length of the cavity plus the thickness in millimeter of the wall. What is in the radial direction? The radial direction, be careful. You have the table here. They give you the radius of the cavity. So to calculate the external dimensions of the chamber, you need to take the diameter of the chamber plus 2 times the thickness, up and down. It's 2 times R plus T wall. The wall is the thickness of the wall. You get 7.2. Which one is bigger? You have the longitudinal dimensions is bigger, so you use in the equation D as 23.5 because this is the biggest one. Okay, you get 49.8 millimeter. Conclusion. The conclusion is that, the conclusion is that to the chamber to be used for the MSR dosimetry of your MSR fields, the fold width at half maximum of your field size should be bigger or equal to 4.9 centimeters. That means that this chamber is not allowed to perform the MSR dosimetry of MSR fields smaller than, let's say, 5 centimeters. Okay, 4.9 is 5 centimeters. Whenever you have a field size down to 5 centimeters, you can use this chamber. If it's less, you use another smaller chamber. Okay. Actually, in the table, they say that this is 6 centimeters. Just to be on the safe side, this chamber can be used only for MSR fields bigger than, higher than 6 by 6 centimeters. Okay. Just to give you another example for semi-flex chamber, we use the same calculation. You will find this in the presentation that I will share with you later on, inshallah. So with the MSR, with the semi-flex, the dimensions are smaller than the farmer type chamber. So we're just calculating the longitudinal is 7.2, the radius is 6.92. We still have the dimension of the longitudinal is 7.2. So the FWSM should be bigger than 32.8. It's 3.3 centimeters. It's already smaller than for the farm. This chamber can be used down to 3.3 centimeters. Let's say 3.5 to be on the safe side, or 4 centimeters. Okay. What happens for the pinpoint, whose volume is smaller? For the pinpoint, the dimensions are 2.9 millimeter compared to the 23 millimeter of the farmer. The radius is 1.45. If you calculate here, you still have the the longitudinal dimensions are 3 millimeter. The thickness of the wall is different than the farmer. It's 0.089, it's 0.1. Okay? And then here you have also for the pinpoint, you have 2.9 centimeters. Okay, I hope that. Please just I recommend that you go through the protocol and do these calculations in order for you to be familiar. Okay, I guess let me just calculate again. The T wall is 0.08. Sorry, 0.085 divided by 1.19. Okay. You got 0.07. Okay. I think the error is here. It's 0.1. Okay. We around this to 0.1. Okay. So it's clear. Not all the chambers are ready for MSR dosimetry. Each field, whenever you have a field size, you go measure you scan your field, calculate, you have the B profile, calculate at 50 centimeters, calculate the length, the fold width at half maximum, okay? And then keep it written down. Go to your chamber, okay? And then calculate the lateral charge particle equilibrium radius using the TPR. It's very important. TPR. Once you get the LCPE, just apply, calculate the dimension, the external dimension of the chamber. If you have a caliper, just measure physically the dimensions, the diameter and the length. It's as easy as like this. And take the biggest one, either the length or the diameter, and replace it in the equation. Calculate the FWHM. Calculate the 2 times RLCPE plus D, and then decide if this chamber is suitable for your field that you scanned, that you calculated or not. Okay, and then you decide. Okay, so this is clear. Now let's just go and remember that for the reference dosimetry of MSR, we have to use the Q0. These are the factors that depends on the TPR 2010 and percentage depth dose at 10 centimeter depth for a field size of 10 by 10. Okay, this is very important to keep in mind that the TPR here is TPR 2010 for 10 by 10. My God, how am I going to now to get the TPR 2010 for a field size of 10 by 10? My machine is not able to achieve this field size. It's a problem. I have CyberKnife. My diameter is 6 centimeters. And this table it is given as a fraction of TPR. So I'm stuck. No, you are not stuck. Because the code of practice is giving a formalism, clever formalism, that will allow you to calculate to get the calculated TPR 2010 for a field size 10 by 10, starting from the measured TPR 2010 for your MSR field, for your field size. Okay, so this is what we do. We actually just need to measure the TPR 2010 for your field size using the same methodology described in the protocol and described in the TRS483. The TPR 2010 is measured by taking 2 subsequent measurements at 10 centimeters and at 20 centimeters, keeping the distance source to detector distance constant as 100 centimeters, or as close as possible to 100, and keeping the field size at the depth of measurement as 10 by 10, or here S by S, S being the field size for your MSR. Okay. Okay. So how you can measure this? You know that you perform the measurement at, just put the chamber at 10 centimeters, okay? And then when you do measure the 10 centimeters, you need to move the chamber at 20 centimeters. If you move the chamber at 20 centimeters, the distance from the source to the detector changes. So you need to move the phantom up by 10 centimeters to bring the detector now, which is at 20, to bring it at the same distance. So this is the first method. 10 centimeters, move the chamber at 20 centimeters, and move the phantom by 10 centimeters to keep the same distance. The other method to measure the TPR 2010 is to perform the measurement at 10 centimeters and then fill in the phantom with additional 10 centimeters of water. In that case, your chamber is still at the same distance. The field size is still the same. Okay. For the percentage depth dose at 10 centimeters, you need just to measure the beam profile. The percentage depth dose, and go at 10 centimeters. Get the percentage depth dose at 10 centimeters. The methodology to measure this is just to keep the chamber to surface distance as 100 centimeters. The field size at the surface is 10 by 10 or S by S, or the conventional MSR field size. And then move the chamber and perform the measurement at different depths and get the percentage depth. Okay. For machines that cannot achieve 10 by 10, the formalism will give you the TPR 2010-10. This formalism is valid for field sizes between 4 to 12. It was proposed by Palmans in 2012. Actually, he took the data from the BGR 25, which publishes extensive data, experimental data. So he calculated this equation actually reproduces the calculated data within the uncertainties established. If you go to the publication, you can see more details. Here, this equation gives the TPR 2010 for a field size 10 by 10, starting from the TPR 2010 for MSR field S. And here, D actually, here this is not, this is D actually. D is just one parameter. So this is very clever equation that modelize the data with just one parameter. The same for percentage depth dose at 10 centimeter for a field size 10 by 10, which is obtained for using the quasi-similar equation. Remember here that S is the MSR field size. This is the square equivalent MSR field size, because this equation is valid for square fields, okay, only for field size. So we have now what happens when I take either circular field size or rectangular field size. I have to use this equation, but S is actually the square field size. It's equivalent square field size. So the protocol, once again, is helping you, saving our life, because this table 15 and 16 is giving the square MSR field size in centimeter for rectangular and circular fields, okay, for WFF and for FFF on the left, for WFF on the right, for FFF. Okay, you need just to take the X or the length and the X and Y, and the intersection will give you the square MSR equivalent field size. Okay, let's do some exercise here. Okay, I will just, yeah. Now we are combining the two exercises, the TPR and the square equivalent. I am giving you here the data that we collected on Electa Versa HD so we have to compare the calculated TPR 2010 for a field size 10 by 10, starting from the measurement of TPR 2010 for a field size S, to compare it with the measured TPR 2010 for field size 10 by 10. So we start by measuring the TPR 2010 for a field size 10 by 10. We set our field size at 10 by 10, and we perform two measurements, 10 centimeter, 20 centimeter, using the configuration that I showed, by moving the phantom or by adding additional water to achieve 10 centimeter and 20 centimeter. So you get here, so actually we have, remember, for the measurement of TPR, this is the ratio, TPR 2010-10 is the ratio of the chamber reading at 20 centimeter divided by the reading at 10 centimeter, corrected for the influence quantities, temperature, pressure, polarity, and recombination. It is actually time consuming. Sometimes it's boring, but you need to do it to get as correct as possible your results. So here we measure that 300 volt, which is the usual polarity of the chamber, and then you measure at 100 volt to get the recombination factor, or saturation factor, and then you measure at minus 300 volt to get the polarity factor, and again measure it at 300 volt just to take the average for the reference dosimetry. Okay, when you take this for 10 centimeter, for 20 centimeter, I leave it to you to do the calculation, but here will trust me, the KTP is given here, the polarity and the recombination. So the reading, the corrected reading for 10 centimeter measurement is 30.3599 nanocoulomb. This is measured for 200 monitor units. Okay, we have to repeat. We repeat the three readings. You can repeat. You can do it if you want more accurate measurement. You repeat 5 times or 10 times. It's okay, but you take here the average and you correct the average by the KTP, polarity, and the combination. This is the result for the 20 is 20.75, etc. So the TPR 2010 for this field size 10 by 10 is the ratio of the two readings. It gives 0.6837. I keep the 4 digits that for the comparison later on. Okay. Now I need to go apply the Pallmann's formalism. I have to measure the TPR for 5 centimeter by 10 centimeter. This is the rectangular field size. Okay. So I do exactly the same measurement. Okay. And I get the correct reading 2.8, 1.9, etc. The ratio, now the TPR 2010 for my field size, which is 5 by 10, is equal to 0.668. You agree with me that 0.668 and 0.6837 are completely different. Of course, because this TPR is measured for my MSR feed. I assume that this is MSR feed 5 centimeter by 10 centimeter. Okay, let's say, assume that this is the, yeah. Okay, now, how am I going to calculate? Yes, Abdelhai.
We have 10 minutes to finish. You have 2 to 3 minutes to finish the presentation, and we have one question for you.
Okay. So just remember, these are the questions for the KTP, for the saturation, etc. So the calculated TPR is by using this equation here. Okay, and then be careful. The TPR 5 by 10. This is you have to use this equation here. S is the square equivalent field size. It's not the 5 by 10. It's not the product. It's not the ratio. It's the square equivalent. If you go to the table 15, the intersection between of 10 by 5 gives 6.8 centimeter. So this is the factor that I have to replace in this equation. 6.8 centimeters. Sorry. And then this one. Remember, this is 16.5 times 10 minus 3. Be careful. Many people forget to multiply by 0.001, which is here. I get 0.6842. So the calculated TPR, the calculated quality index, which is TPR 2010 for hypothetical field size of 10 by 10 is 0.6848. What is the difference? The difference is 0.07%. So this shows that the formalism is perfect. It's assume that you are not able to measure the TPR 2010 for 10 by 10 for tomotherapy, for example. Just by measuring for 5 by 10, you can calculate the hypothetical quality index for the field size 10 by 10 is 0.07%. Okay, I'm just giving you here some results for that we measured for tomotherapy. It's within 0.2%, 0.1%, etc. Okay. Yes, I think Now, just to finish, I would like to give you some example of the reference dosimetry. For the reference dosimetry, remember you have this formalism. So our chamber is the farmer chamber. This is the calibration coefficient for cobalt-16, and this is the quality index that we measured. Okay. So the problem here, the KQQ0, this is a quality correction factor that needs to be calculated for your TPR. Or, however, the table is giving for the quality index 0.66, 0.99, 69, 0.72, and 0.75, which are around 6. This is 6 MV, and this is around 10 MV. Okay, so I need to interpolate the data for my chamber. The linear interpolation is enough accurate. Okay, when I interpolate the data for my quality index, I get 0.99, and then I need just to move to the equation here. Okay, so the rating is 30.3599 from the previous measurement of the TPR 2010. Remember, this is 10 centimeter for 300 volt, corrected for polarity recombination and temperature. So I get 30.37 divided by 200 monitor unit in terms of nanocoulomb per monitor unit, and then I calculate the dose, and I get 0.81 centigrade per monitor unit. So this is the way that we do. We need just to. It's crucial to interpolate your data using TPR, the two values here. You can use the linear interpolation. Okay, so you have only two data. You can use. You can also, if you can plot a curve giving the KQQ0 as function of TPR and use this equation to generate or to interpolate. Okay. Yes, just to move to I need just to explain one thing. When you move to the determination of the feed output factor, so this is actually the ratio of the rating for the F-clean, the clinical field size, divided by the reference field size, which is 10 by 10, multiplied by the KQ clean QRF, which is the feed output correction factor. It is important to the feed output correction factors are given in the code of practice as a function of the square field size. How you can calculate the S, which is the S-clean, which is a calculated square equivalent field size. We just use this for the rectangular field size. It's the square root of A multiplied by B. For circular field size, the clinical square equivalent field size is given by R multiplied by square root of pi. The A over B for this formalism here, or this equation here, is valid when the ratio of A over B is between 0.7 and 1.4. Okay. The equation here, this table is giving the feed output correction factor for equivalent square field size, S-clean. So you need to calculate if you have, for example, let's say 4 times 4 by 5, a rectangular field size of 4 by 5. So what is the S-clean? It's square root of 4 times 5, the square root of 20, which is 4 point something. Okay, a square root this for a circular field size of let's say 5 centimeter diameter. It's 5 centimeter multiplied by square root of pi. Okay, so these factors here you can use an interpolation if you have, for example, any S-clean for your machine. And you have to interpolate your data using this. This is the equivalent square field in centimeter, and these are the corresponding field output correction factors for any detector that is included in the code of practice. There is one particular detector where the field output correction factor is 1. It's just in the bottom of the table. These are the standard imaging W1 plastic scintillator. This is the magic detector. When you measure the output factor, the ratio of the readings, you don't have to multiply by any correction factor. It's already the feed output factor. It gives an idea. If you measure, if you have a detector for which you don't have the feed output correction factor, you just, and if you have the W1 chamber, there is another one which came after this one, is W2, which is even more interesting. Then you have to measure 2 output factors in terms of ratio of readings. You measure the output factors with the scintillator. The comparison will give you the feed output correction factors. I had the chance. Yes,
it's time, Mr. Arib.
Yeah. Okay.
We have 2 important questions.
Yeah. Thank you. I feel here. Anyway, I finished already. Okay, just go ahead with the question, please.
Because there is another webinar start at 8. Okay. The first question is from Mr. Salah Bali. What about gamma knife and cobalt 60, the 2 radius of lateral equilibrium without adding the dimension of the chamber is bigger than 2 centimeters, and the MSR field size is 1.6 to 1.8.
Yes. Actually, for the gamma knife, the protocol is publishing only, I think, only 2 detectors are allowed for the gamma knife. I think the pinpoint.
باختصار مستر عارف يوجد سؤال آخر. There is another question. باختصار.
Yes. خلاص. In the code of practice, they give you the chamber, they give you the correction factor, and you have to measure the reference dosimetry just using a special phantom using this chamber. You cannot use any chamber. For this chamber, the correction factors are published in the protocol. You need to stick to the chamber that is in the protocol. Yeah.
Okay. Second question is from Grand Blue. I have one question. The MSR field of the gamma knife model perfection is 16 millimeter. The dose rate is measured in this field with the pinpoint chamber, and the output factor for the 8 millimeter and the 4 millimeter are determined using Monte Carlo simulation. My question is why the GAF chromic film EBT3 is not considered as reference dosimeter for the small field, since it has good characteristics, high spatial resolution, tissue equivalent, and also it presented a good result when measuring the output factor comparing with Monte Carlo simulation. This is
yes. GAF chromic, I think the GAF chromic film are not used as a reference detector, because first of all, you have for the GAF chromic film, we have the problem of the calibration. You need to calibrate it for a specific machine, and it doesn't have a linear behavior. It's a curve. And secondly, if you read your as reference, if you use it, if you use 2 sheets of GAF chromic films, you will have the 2 different results. It's not like the conventional detectors. This is very, very important. So we use the GAF chromic as only for relative measurements, just for the output, not for as a reference. Yeah. It depends on many factors. It depends on when you scan the GAF chromic film. If you use 3 different scanners, you get 3 different readings. Which one are you going to use? So you have to stick. If you want to use it as a reference, you need to calibrate it for this machine. You need to use the scanner in the optimal conditions, and you need to use the same the same scanner, use it for the calibration, for the relative measurement, and for the dosimetry. I haven't. It can be also the uncertainty. I think the uncertainty in the dose measurement with the gas per mic is much more higher than the in the reference dosimetry is higher than the other detectors.
Yes, that's.
Yeah.
Thank you, Dr. ARIB. The most comment is that thanks for you for this very important lecture. And for example, the last comment is from Mr. Islam Mahmoud Rizik. Hope if Dr. ARIB give us another lecture, build up the knowledge from this lecture. Also, there is other from another comment from Prof Moussa. Est-ce que nous pouvons avoir cette présentation en PDF, etc., etc.
Oui, on peut l'avoir. We can. I will share with Abdel Hay the presentation in PDF, and then of course there are some data here, for example, that are not yet published. We can remove them. The last data, which are the results of our machine. But for the rest, I can send you the PDF. No problem at all.
Anyone would like to take this presentation in PDF format, you have to contact our two emails, one of the two emails. Okay, Dr. ARIB, so thank you so much, and we're looking to another lecture, inshallah, in this field.
Inshallah. It was a pleasure for me to give this lecture. I hope that I'm seeing here that we had 53 participants. It's already a good number, because the community of medical physics is not that big. So I guess that there are many participants from outside Algeria. I'm very happy that I contributed a little bit to the knowledge of a medical physicist. My email is known by everyone, and you have my contact. I can share it. There's no problem at all. If you have any question, or if you request any documentation from me, just send me a private email, and it will be a pleasure for me to share with you the documentation. Thank you very much. Thank you.
Okay. شكرا جزيلا مستر عريب. كذلك لا أشكر جميع الحاضرين على وجميع المتدخلين. إن شاء الله نراكم قريبا إن شاء الله في our second webinar next to January إن شاء الله 2021. عندنا إن شاء الله مفاجأة في الويبينار القادم إن شاء الله، قامة من قامات الجزائرية، وإن شاء الله نراكم بخير بإذن الله. السلام عليكم ورحمة الله.
السلام عليكم.
شكرا جزيلا.